Good afternoon, everyone. Thanks, Ian. Thanks for the invitation to come and speak. I'll give you a quick 20-minute talk about some of the issues that are facing bridge owners, and specifically on Forth Road Bridge, on maintenance of large structures, which are very important in the sustainability agenda because we don't build many of these things anymore. So we've got to make sure that the ones that we have are maintained properly, and to ensure that, they've got to be funded properly. I'm a civil engineer by profession, and I've been involved in the maintenance, design and maintenance of bridges for quite a while. This is perhaps the most famous bridge in the world. You'll all recognize it. It's Golden Gate, and it's fitting that it's in the US because the US is where long-span bridge engineering started. In 1883, Brooklyn Bridge was opened. It was designed by an American civil engineer called John Roeblings, and he developed a method of spinning cables which revolutionized bridge engineering and revolutionized life in New York and throughout the world, I would imagine, because it enabled the bridges on the East River and the Hudson to be spanned, and that opened up Brooklyn and other areas of New York and made it develop into a city. So it was a very important innovation, and that was way back in 1883 by Brooklyn, and we're still using the same techniques today. In 1937, Golden Gate was opened, and it's 1,280 metres span, but the same techniques were used as Roeblings used in 1883 to build this magnificent structure. And I have to say, my colleagues at Golden Gate, same with all colleagues throughout the world, face the same issues with maintaining these structures. They need funding. There are over 100 people working on the maintenance of Golden Gate Bridge every day to keep it going, to provide the service that it's required. This is perhaps should be the most famous bridge in the world. This is the Akashi in Japan. It is 1,991 meters between those two towers, almost 2 kilometers. And when the Kobe earthquake struck in 1997, the two towers had been erected, and the two towers moved apart by just under a meter as a result of the earthquake. So engineers, as usual, just did what they did and extended the size of the length of the deck and the cables, a bit of redesign. And the bridge was opened in 1998. Still stands as a tremendous monument to engineering. It's the longest span bridge in the world. One of the things I have to say is that the relationship between design, construction and maintenance is an important one. We're all aware of the relationship between design now for safe and cost-effective construction with CDM regulations, etc. But there is a relationship between design and cost-effective maintenance. I'm not quite sure that we've realized all of the opportunities to design to make sure that maintenance is relatively or as easy as possible in the future, especially with access. I think there's still a lot of work to be done there. I'm not quite sure either that the design and construct form of contract is actually amenable to future maintenance of these large projects. Things do go wrong, unfortunately. This is a suspension bridge which collapsed last year or the year before in Indonesia. Several lives were lost, so it's important that not only design but maintenance is carried out on these structures. Quickly moving on to the bridge that I'm responsible for looking after. This is Forth Road Bridge. It sits beside its perhaps more famous neighbour, the Forth Bridge, or Forth Rail Bridge. It's on the Forth, which is just north and west of here. Many of you may have crossed it. It crosses the Firth of Forth, a major crossing when it opened in 1964. It's over a kilometre between the towers of Forth Road Bridge, which makes it still one of the largest bridges in the world. It was the fourth longest when it was opened in 1964. The other three were in the United States: Golden Gate, Mackinac and George Washington. So it's a substantial structure. We're now on 26th on the list, I fear, because bridge engineering has developed across the world. The centre of long-span bridge building moved from the US to Europe, then to Japan, and now it's in China and Korea and elsewhere. There's a large cable-stayed bridge being opened in Vladivostok sometime in the next couple of years with a 1,200-metre span, which is quite extraordinary. But Forth Road Bridge, these bridges are very flexible structures. The centre of that span in Forth Road Bridge, right in the middle there, in its design wind, will move 7 metres laterally. With the full traffic loading on it, the mid-span will drop about 4 metres. For a 25 degree Celsius change in temperature, if The temperature rose 25 degrees today, which would be quite something. The main span there would sag down by 1 metre, and then if the temperature started getting colder again, it would drop by a metre. It makes trying to determine the navigation span or the navigation under clearance under the bridge quite an interesting exercise. It takes a lot of looking after, and sustainability is a big part of our agenda. This is the truss underneath the bridge. It was one of the last big trusses to be built. Box girders came into fashion with and became the selected choice for decks because of their structural capabilities. Trusses are good fun, but they take a lot of looking after. There's 200,000 square metres of paint, surface paint area on that truss. Now the truss is painted with very high solvent-based paints. High solvent-based paints are environmentally fairly unfriendly, but they're fantastic as far as painting structures are concerned, because the next coat goes on to the last one without much preparation. You don't have to take any paint off, if any. Unfortunately, they have a high solvent content, and they're now effectively not produced anymore because European manufacturers can't produce more than 5 tons of solvent a year. Therefore, these paints have gone completely off the shelf as far as painting steel structures are concerned. We've now got epoxy paints, but regrettably epoxy paints don't work on these, so you can't overcoat, they just fall off. So when we have to paint this structure, which we'll have to do in the near future, it will cost us £65 million to paint the truss, simply because we have to take all the paint off to enable the new paint to stick onto the steel. Now that's got an environmental impact on its own. So the balance of banning high solvent paints has a downside, and this is a downside, unfortunately. We have to provide containment, we have to provide access for that containment, and we have to get rid of all this old paint once it's finished, and we'll probably end up with less of a job than we had before, so it probably means we have to go in and do it more often in the future. So there is a downside. Access is always an issue. We have to get up and find and look at things, bolts, welds, cables. These are 2 of our inspectors nearing the top of the particular journey up the side span main cable, and George at the front there is obviously feeling the pace a bit, stopping for a quick rest. I have to say he doesn't normally pose for the cameras. That grimace is really him stopping for breath. Monitoring of these bridges is quite extensive now. And monitoring is obviously a key for us to enable us to find out what's happening with movement, with stresses, etc. But you still need people to go up and have a look, because one of the issues with monitoring equipment is that you end up having to maintain the monitoring equipment, which is there to try and minimize the amount of maintenance that you're trying to do in the structure. The main cable is an issue that we've had to face over the past 10 years in the bridge. Main cables and suspension bridges are made of, in this case, 11,618 individual 4.98 mil diameter high tensile wires. Bridge wire is very, very strong. It's got high ultimate tensile capacity. Unfortunately, the stronger you make steel, the more sensitive it becomes, and the more likely it is to brittle failure. The wire spec is around about 1,600 newtons per millimetre squared, 600 millimetre diameter. It's then compacted and has a wire wrapped around it and then painted. Red lead paste put in before the wrapping wires put on. That was 64, exactly the same design as Roebling's in 1883 in Brooklyn has been used in all of these bridges. Loading has also changed. Dead load hasn't changed much, neither super dead load, but live load has significantly gone up from about, as you can see there, about 15.5 kilonewtons per metre run to something like 27.5, and that's not an assessment load. That's not the national UK assessment load. That's a bridge-specific loading. That's a much reduced loading. So we've had to look at all these things for keeping the bridge going and fit for purpose. Footway loading we felt was a bit high at 4.5 kilonewtons per metre, so we're looking at a controlled loading of 0.3. A lot of work in the States about cable, a lot of worries in the States in the early 90s and into 2000 about states of cables. They've got older bridges, and the National Academy's produced this report, and we used that to carry out an investigation into the main cable at Forth Road Bridge. It was 40 years old, showed no sign of corrosion on the outside, but as a principal structural element, we felt we had to have a look inside. First inspection was 40 years. After 40 years, we carried out a second inspection in 2008, and we've just completed the third inspection. These things cost money. They cost about £3.5 to £5 million, and you're looking at a very limited amount of the cable, a very limited population, very small sample, and from that small sample, we're having to make pretty large engineering decisions. It's easy to do it at low level, but at high level, it gets a bit more tricky. And the whole concept is not to interrupt traffic. There are 24 to 25 million vehicles a day using Forth Road Bridge. It's crucial that we don't interrupt that flow, because anyone who has or does use the bridge knows that even if a lane's out during the day, there's significant disruption for hours before you can get across. So everything's designed to be contained, to make sure that interruption to traffic is minimized. That's one of the platforms getting ready to be lifted up. That was done on an overnight closure, and there's the inside of a platform. Costs, as I say, pretty expensive, and that's what it looks like inside when you unwrap and wedge open a main cable. Before I saw it happening, these are the 11,618 wires. You take the wrapping wire off, and you start with a small brass chisel and a small hammer, and you start gently tapping away until you get an opening, because you don't want to nick any of these high tensile, and they are galvanized wires. And then you get the biggest block you can find, the biggest hammer you can find, and you get some wooden and plastic wedges, and you do this, and you open it up all the way around the cable. Unfortunately, we found something that we didn't expect to find. We found broken wires and quite significant corrosion, but one of my colleagues from the States said, don't worry about that. When we opened one of the bridges in Philadelphia, I won't name it, they had hundreds of wires falling out, so that provided some comfort for us. That's what it looked like inside. Certainly not what we expected to find. Quite a degree of corrosion, so it looked good on the outside, didn't mean it was looking good on the inside. These are the corrosion states from the NCHRP, and all the stage 1 wires where it's galvanizing still there want to do is become stage 2s and it just bumps along the bed. Unless you can stop it happening, unfortunately, as the man said, corrosion doesn't or never sleeps. All they want to do is progress along the stages. We had brittle failure. This isn't a nice elastic failure of the wire. This is corrosion pit occurs, crack happens, wire breaks, or wire cracks, corrosion pit occurs, wire breaks. Whatever happens, the wires break eventually. This is what it looked like in a cross section. The arrows are the wedge lines. The red is bad, that's stage 4, and we didn't expect to see as much of that. Not so many broken wires in that panel, but a lot of corrosion. We took samples, and then we had to rewrap it, and we used the last red lead paste in 2004 from the New Amsterdam works in New York that were ever produced in, I think, in the Western Hemisphere. If you want red lead paste, you have to go to China now, which is the compaction machines alone, I think, cost us $100,000 to design and build a new compactor and a new wrapping machine. So the conclusion was, if it looks good on the outside, doesn't mean to say it's good on the inside. And we need to rely on research and development for these components and bridges, and new techniques to try and stop such corrosion happening. And what we did was fit acoustic monitoring to monitor it along the bridge. These are the acoustic monitoring points. These don't actually help stop corrosion, but they give you an idea of wire breaks. How much of an idea is perhaps open to question, but they provide some benefit. We looked at what do we do then to stop this corrosion. The Americans had started oiling cables, which to me looked not quite the right solution. This is a bridge, and this is Ben Franklin in the States, and it just looks a bit of a mess actually. I don't think it works. So we looked at the methodology of dehumidification, pumping dry air at low pressure into the cable to try and drive out moisture. Takes a lot of kit, pretty new technique. Japanese had developed it for their newer bridges, but we took it a stage further for an older bridge. System layout, you pump dry air in, and it just has to be dry air, it doesn't have to be anything else, at about 3,000 pascals, which is pretty low, using a dehumidification equipment and pumps, and let it slowly work its way up the cable until you get to an outlet point, perhaps 200 meters away or so, and eventually you hope that all the moisture will be driven out, because as we know, corrosion is caused by two elements, and if you can get rid of one of them, and we decided moisture was the key one, then you can halt corrosion. It takes a lot of work. This is yet another platform, a different one from the last slide. I have a wide selection of used main cable platforms. If there's any interest out there, I'd be happy to enter negotiations. It doesn't seem to be much of a market for them. Everyone wants to design their own. Although, to be fair, Humber Bridge did use some of ours. But cables are all different diameters, hangers are different centers, so it's very difficult to reuse them. The cable's wrapped in the outside before the dry air is pumped in. It's all web-based monitoring system. It was done under a fairly local scrutiny with the media. The media love a good bad news story. As a local journalist said to me, there are only two stories about Forth Road Bridge he's interested in. That's one is safety fears, and the other is traffic chaos. If the headlines don't have those in it, then he's not interested. But that's the way it is. The giant hairdryers was a good one. We couldn't persuade them that these weren't hairdryers. This isn't warm air, it's just air, but hairdryers is far too good a headline. You can't, who can blame them? So this is, and there was a lot of opposition to it, because the government decided that given that we couldn't give them an unconditional guarantee on the condition of the main cable in the future, the government decided that they would have to go ahead with and get some resilience in the system and build a second crossing. We've just carried out our third inspection post-dehumidification. The results are just out. That's a lot of text on there, but basically it's to say, in case there's any journalists in the room, it's to say that the factor of safety against failure of the cables has not materially diminished since we last looked in 2008, and the dehumidification appears to be having an effect. So we're fairly happy with what we've found. There is still some slight deterioration, but the dehumidification appears to have slowed it down, and this is the graph that we don't show anyone, so this is for your eyes only. The numbers are completely, the fact that it's to 2 decimal points is just because the young graduate who did it loves 2 decimal points. I keep saying to him that 1 would be fine, but he loves 2. In any case, it's very simple. Cable factor of safety up the left-hand axis, number of years along the right-hand axis. We started off somewhere about 2.64, and this is, don't worry about limit state or any of that kind of stuff. This is the basic factor of safety. What's the load, and what's the ultimate capacity of the cable? This isn't against yield. This is against bang. This is against the cable failing. There's no yield in this. This is equivalent to about 1.75 or 1.8 as a factor of safety against yield. So this is against ultimate failure. Started off at 2.64. 2004, we reckon we're at 2.28. Curve fitting, you can see there, is quite an art when you've only get to point some 40 years later. And then in 2008, we thought it lost a little bit more. And then 2013, we think it's lost just a little bit more, but it's all flattening out. And the green line is where we don't want to go to. Factor of safety of 2 is our target, to keep it above that. Why 2? Well, it's better than 2.05, and it's not as good as 2.05, but better than 1.95, I think is the answer to that. Sounds a good number. What happens if it didn't work? Well, we carried out a study, and you can replace cables in suspension bridges, but it would take about 9 years to do. You'd have to have severe traffic restrictions to minimize the risk to users. Of course, you can do it by closing the bridge. You could do it in 3 years, but that wasn't politically acceptable. The other thing that we've been looking at recently is the main cable anchorages. These are where there's 13,500 tons in the anchorage. Suspension bridges are fairly simple structures. You've got a cable and all the load, the bridge and the deck, everything's hanging off the cables. It goes over a pair of towers, and then it goes into anchorages. All the load either goes down the towers or into the anchorages, nowhere else for it to go. They're very highly non-redundant structures. If you lose a main cable, you lose the bridge. You lose a tower, you lose the bridge. If you lose an anchorage, you lose the bridge. So they're very highly non-redundant, very efficient, but highly non-redundant. And we had an issue with the main cable anchorages. They were built in post-tension tunnels back in the 60s. That's a kind of schematic of it. You can see it. The cable comes down into a chamber at the bottom there, and then is anchored at the face of a tunnel. And the tunnel, as we all know, concrete's not that great in tension, so what did they do? They decided to post-tension it, and this is in 1960-61. And as we all know, we've had problems with post-tension decks, and that's above ground. So the fact that we had post-tensioning in a highly saline environment didn't augur well, and we didn't know, there was no way of inspecting them. The tendons look like that. Again, they're galvanized. They're 4 tendons, 4 strands in one tendon and a steel duct with grout between them. And the bit that really worried me anyway was this hole in the middle. How do you get grout up there? These tunnels are about 70 meters long. This is it being built. That's what it looks like inside the anchor chamber. You can see the wires coming round to the strand shoe, and the heads of these 6 groups of 6 are the socketed heads of the post-tensioning strands, and they've got about 150 tons in them. So what do? We needed to find out the condition of these because we were pretty worried about them. We looked at all sorts of testing methods, ultrasonics, acoustic monitoring, radar, everything. No one could give us any real techniques that we thought would work, so we decided, well, we'll just have to dig a big hole and have a peek, because that seemed to be the only feasible way. The only thing was we had the viaduct pier next to it, so we had to deal with that. And it's only about 7 meters down. So what we're trying to do is get down and expose the top strands in the tunnel, and that's how it is at the moment. This is a £5 million investigation. You can see the back of the anchorage chamber, and those down at the bottom there, those are the ducts which are exposed. And what we have done is we've carefully cut the ducts open to expose and washed out the grout to expose the tendon. And we know the answer now, but I can't tell you, unfortunately, because I need to report to the board, my VETA board, next April, but we should have the results then. That's what it looks. That's what the ducts look like in the mass concrete. We've exposed them at the top, and we're doing all sorts of work to X-ray them and magnetostriction on them, on the ducts as well, and on the strands. What happens if it was all pear-shaped, everything went wrong? Well, there's a nice schematic of the existing tunnel with the cables coming down. We were just going to build a new anchorage if someone would give us some money at the back there. So and that could be done without closing the bridge. All you have to do is build a big diverter frame, take a strand at a time, and then put it into build your new anchorage firstly, of course, and then attach them on strand by strand with traffic still running. This is the future. The new crossing is being built even as we speak. The foundations are going in. That's the existing bridge on the left, the new bridge on the right. The towers of the cable-stayed bridge, as you can see, are about 50 meters above the existing bridge towers. It's one of the differences between the two forms of structure. You need large, tall towers for cable-stayed bridges. It's about a 650-meter span between the towers. It's a 3-tower bridge, which is fairly unusual for cable-stayed bridges. The big difficulty is how do you get stiffness into the system with the center tower, because it's stayed back to the suspended portion. And they've done it, in this case, by crossing the stays, which is fairly unusual. Thank you very much, ladies and gentlemen. I'll just finish by quick plug. We're holding a conference in 2013. Anyone wants to come along and listen to bridge owners with their particular issues and problems throughout the world, you'll be happy to see you out at the Sheraton on the start of June. Thank you.